Hello and welcome to the 2022 US SPDK Virtual Forum. My name is John Kariuki and I'm a cloud software development engineer at Intel. And in this talk, I will be talking about the work that the SPDK community has done to provide strong error detection for the NVMe over TCP Protocol Data Units with hardware accelerators such as the Intel Data Streaming Accelerator, also called Intel DSA. So my talk contains performance data. So here are the notices and disclaimers. And if you want to see the details of the configurations, they're in the backup. I believe they're in slide number 20. So here's what the agenda looks like. So I'm gonna start by talking about NVMe over TCP data digest, right? We're gonna go over a quick intro of what the NVMe over TCP data digest is, and then once I am done with that, I'm gonna share the test environment that I used for my testing, and then I'll show you the different configurations that we tested in our benchmarking, and then we're gonna wrap this up by looking at some test results showing the type of performance and efficiencies that we're measuring with offloading the data digest computation to Intel DSA. So let's get started. So let's take a look at what NVMe over TCP data digest is. A host and a controller in an NVMe subsystem communicate over TCP by exchanging NVMe TCP Protocol Data Units, or PDUs. And the PDU can be used to transfer capsules, data, or control status information. As I'm showing here on the diagram to the right, the PDU can have up to 5 parts, and one of the parts is an optional data digest field that may be included or omitted based on either the PDU type and the values exchanged during the establishment of the connection. Now, if that data digest field is enabled, the digest will be calculated using the CRC32C algorithm in the RFC 3385. And then it will be added to that data digest field that's at the bottom here of that diagram that I'm showing, that DDGST field. What we're doing in our benchmarking, what our objective was to measure that incremental overhead of calculating that CRC32C with software on the CPU cores that are assigned to the target application. And then once we measure the incremental overhead, we configure the target application to offload that computation to Intel DSA and compare the performance and efficiency of offloading that CRC32C calculation to Intel DSA versus calculating it using ISA-L on the same CPU cores that are assigned to the target application. So now let's take a look at the test environment. The target is running on that system that I'm showing here on the right, which is really just a standard 2-socket Intel system. It has 2 4th generation Intel Xeon Scalable processors, codenamed Sapphire Rapid, and each of those processors have 1 DSA device. So we have a total of 2 DSA devices on that target system. The target system also has 16 NVMe SSDs, and those are evenly split between the 2 sockets. So we have 8 NVMe SSDs per socket. And then the target system also connects to two initiator systems over two 200 gig NICs, and these are the Intel EA10 NICs. And once again, those are set up in such a way that we have one NIC on each socket. And then on the initiator system, we're running FIO. We're running it in server mode on each of those initiator system. And we're doing that so that we can submit IO requests from those initiator systems to the target system concurrently. So as far as the IO path goes, the way the IO path is set up is such that it starts on the initiator side with FIO, sending a request to read data from NVM subsystems that reside on the target system. And when the target gets those requests to read those IOs, the target goes out to the NVMe devices, it reads the data from the devices, and then uses the acceleration framework to compute the data digest. There are two methods that the acceleration framework uses to compute that data digest. If during the initialization of the target application, an RPC was issued to tell the target that it can offload certain operations to Intel DSA, the target will offload the CRC32C computation to Intel DSA. Otherwise, if offloading to Intel DSA wasn't enabled during initialization, the target uses ISA-L, which stands for the Intelligent Storage Acceleration Library, to compute the CRC32 digest on the CPU cores that are assigned to the target application. And then finally, once the target has computed the data digest, it puts the data and the digest into a PDU and transmits that to the initiator system. As far as our testing objectives go, our objective is really to compare the performance and efficiency of offloading that CRC32 computation to the Intel DSA hardware accelerator versus computing that digest on the CPU cores that are assigned to the target application, where that computation of that CRC32 digest would be competing for CPU cycles with other work that the storage target application is doing, such as polling incoming connections for IO requests, submitting IOs to the NVMe SSDs, and polling the NVMe SSDs for completions. So the way we approach this is we had 3 test configurations. In the first configuration, we just wanted to collect some baseline numbers, right? So we disabled DSA. There was no CRC32 computation being performed. And what this computation does is it really just helped us understand that incremental overhead of calculating that data digest when we finally enabled it. In the second configuration, we enabled that data digest computation and used ISA-L for that CRC32C computation. So ISA-L is the Intelligent Storage Acceleration Library. And what ISA-L does is it provides an optimized implementation of the CRC32C algorithm that uses the vector carryless multiplication instructions that are part of the AVX512 instructions in Intel CPUs. Using ISA-L, what that really does is it enables the target to just work, right? So in environments that don't have Intel DSA, the target application can still provide data protection using ISA-L. So from a data protection perspective, once we enable that, the target just works, whether it's in environments that have Intel DSA or environments that do not have Intel DSA. And then last but not least, that configuration is where we enable the data digest, and we used Intel DSA to calculate the CRC32C digest. For all these three configurations, what we did is we ran tests, we ran different workloads, measured the IOPS, and then computed the IOPS per core. That way we can show the efficiency of offloading to DSA, offloading that CRC32C computation to DSA versus doing it on the CPU cores assigned to the target using ISA-L. So let's take a deep dive into the test results. So in the first test that we did, we configured the SPDK NVMe of a Fabric target application to use just one CPU core. And then on the host side, we had those two initiator systems that we have. We had them submit IO read request. We tested with three different block sizes. We did testing with 4K random reads, 16K random reads, and 128K sequential reads. And for each of these block sizes, we used 4 different queue depths, a queue depth of 8 per SSD, 16 per SSD, 32 per SSD, and 64 per SSD. So since our target system has 16 NVMe SSDs, those queue depths, they translate to a total queue depth of 128, 256, 512, and 1024 on the target side. And then as we were running these tests, we measured the IOPS when the target was using ISA-L and when it was using Intel DSA to compute the data digest. And then we use those IOPS number to compute the IOPS per core. And that's based on the actual CPU utilization that we measured using the Linux SAR command. The table that I'm sharing here on the left is the comparison of the IOPS per core when the target application was offloading that data digest calculation to DSA, to Intel DSA, versus using ISA-L to compute that CRC32 data digest. And what we basically observed is when the workloads, when these 3 workloads were CPU bound at those higher queue depth, we see Intel DSA improving the IOPS per core by up to 34% for 16K random reads, by up to 71% for the 128K sequential reads. And for the small blocks, the 4K random read blocks, we see some gains, but they're pretty minimal. So ISA-L actually performed pretty well for those 4K random reads. At the low queue depth, these workloads were not CPU constrained. And what that means is, since SPDK uses this POM mode design, there were enough CPU cycles for ISA-L to compute the digest, and also for the target to do other tasks such as processing incoming NVMe TCP IO request, submitting IO requests to the NVMe SSDs, and completing those. So the first time when we looked at these numbers, we were a little bit curious as to how much CPU the ISA-L CRC32 function was actually using. And this was especially for those 128K sequential reads at the high queue depth. So what we did is we decided to collect a CPU profile for the target application while we were running the 128K sequential reads, and the target was using the ISA-L CRC functions to compute that data digest. As you can see in the profile that I'm sharing, the ISA-L CRC32 function was consuming over 50% of the available CPU cycles. So pretty good confirmation here that the task of actually computing the CRC32C data digest can be pretty CPU intensive for those large block workloads. So the next thing we're going to look at is the performance and efficiency of offloading that CRC32C computation to Intel DSA as we scale the number of CPU cores that are used by the target application until we saturated that 400 gigabit per second network. The graph I'm showing shows the relative IOPS per core for the target application when using Intel DSA to compute the data digest. That's that green bar versus ISA-L, that blue bar, as we increase the number of CPU cores that the target application was using from 1 all the way to 3. And this is for that 128K sequential read workloads at that high queue depth of 1024. We also added the relative IOPS per core when the target did not compute the digest at all, and that's that gold bar. So as I'm showing here on the graph, on this graph, as we scaled the number of CPU cores that the target was using from 1 to 2, we still see pretty good improvement in IOPS per core when using Intel DSA to compute that data digest versus using ISA-L. As a matter of fact, at 1 core, we measured about 71% more IOPS. At 2 cores, we measured a little bit higher, almost 80% more IOPS per core when using Intel DSA to compute that data digest versus using ISA-L on the CPU cores that are assigned to the target. And then as we get to the configuration where we have the target using 3 target cores, we're starting to get to the point where the network is saturated. So the relative IOPS per core numbers are not as impressive as what we saw with 1 and 2 target cores. When we measured the actual number of CPU cores that were used to saturate the 400 gig network, what we observed on this graph over here on the right is that the target application used just 6 CPU cores to saturate the 400 gig network with data protection. And that's actually the same number of CPU cores that were used when the target did not compute that digest at all, right? So I'm talking about those green bars and the gold bars here on that graph on the right is they are showing us that there are no additional CPU cores needed to saturate the 400 gig network when we used Intel DSA for the data digest versus not computing the digest at all in the first place. And that's because offloading that CRC32 digest computation to DSA eliminates those 3 cores of ISA-L software overhead and reduces the total number of CPU cores required to saturate the 400 gig network by 33%. And in case you're wondering, what happened to the latency when we offload the CRC32C computation to Intel DSA? We did measure the latency, the average latency, and the P99 and the P99.99 latency for the target application, offloading the digest computation to DSA versus using ISA-L. And what we saw for the 128K sequential read workload at that high queue depth of 1024, what we saw an average latency reduction of up to 46% when we used Intel DSA for the CRC32 digest computation. P99 latency reduction of up to 34%, and P99.9 latency reduction of up to 31%. So next, let's take a look at the relative performance in IOPS per core for the 16K random reads as we scaled the number of CPU cores that were used by the target from 1 until we saturated the 400 gig network. So on this graph that I'm sharing, the green bars, they represent the IOPS per core for the target application when the target was using Intel DSA to compute the data digest versus when the target was using ISA-L, which is the blue bars. And as you can see, as we scaled the number of CPU cores that are used by the target from 1 to 6, we see CPU efficiency improvements of anywhere between 24 and 34% more IOPS per core when offloading that CRC32 computation to Intel DSA. So looking at the green bars on this graph versus the gold bars, which represent the relative IOPS per core for the target when it was not computing the data digest at all. What we observed is that as we added more CPU cores, right, as we give the target application more CPU cores and increase the load on the target application, using Intel DSA to compute the data digest eliminated almost all that additional overhead of computing the digest in software with ISA-L. And as a matter of fact, when we measure the actual number of CPUs that were needed to saturate the 400 gig network for the 16K random read workload, we're seeing that it's taking the same number of CPU cores when we have the data digest enabled and we use DSA versus when we don't have the data digest enabled at all. So on this graph here on the right, as you can see, it took 10 cores to saturate that 400 gig network when we offloaded that data digest calculation to Intel DSA. And that was the same number of cores that it took to saturate the network if we skipped that data digest computation completely in the first place. And that is because using Intel DSA to compute the CRC32 digest for the 16K random read workload completely eliminates the 4 cores of ISA-L software overhead that were needed when the digest was calculated on the CPU cores assigned to the target application. And that adds up to about a 28% reduction in the CPU cores needed to saturate the 400 gig network when using Intel DSA to compute the data digest versus ISA-L to compute the data digest. So looking at the latency for the 16K random read workload, when the target was using Intel DSA to compute the CRC32 digest, we observed an average latency reduction of 38% when using DSA to calculate the digest versus ISA-L, and a P99 latency reduction of up to 33%, and a P99.9 latency reduction of up to 19%. Finally, let's take a look at the CPU efficiency for the small block workloads, that 4K random read workload, as we scaled the number of target CPU cores from 1 all the way until we saturated that 400 gigabit per second network at about 11 million IOPS. So looking at the green bars on the graph that I'm sharing here, with the Intel DSA at 1 CPU core, we saw about a 8% improvement in the IOPS per core when the target application was just using 1 core and offloading that CRC computation to DSA versus using ISA-L. When we increased the number of CPU cores from 1 to 4 and 8, 12, and even 16, that CPU efficiency actually went up a little bit, right? So as the target application had more CPU cycles available to use, it's actually doing more work, and as a result of that, it's actually submitting more requests to the DSA device. So in terms of the CPU efficiency at 4 cores, 8 cores, 12 cores, and 16 cores, we saw numbers that were anywhere between 12 and 15% more IOPS per core when using DSA to compute that data digest versus using ISA-L. And when we take a look at the number of CPU cores that it took to saturate the 400 gig network at about 10.8 million IOPS, what we see is that when the target was using DSA to compute the digest, it took about 32 cores on this system to saturate the 400 gig network for the 4K random read workload. And that was a savings of 4 cores versus using ISA-L to compute the digest. So it all comes down to about a 10% reduction in the number of CPU cores that are needed for this workload to saturate the 400 gig network when we enable the data digest and use Intel DSA to compute the digest instead of using ISA-L software. As far as the latency for the 4K random read workload, when we look at the latency at the point where the network was saturated, what we see is that when the target was using Intel DSA to compute the data digest, we observed an average latency reduction of up to 11% and a P99 latency reduction of up to 9% and a P99.9 latency reduction of up to 7%. And to summarize our benchmarking effort, we observed significant gains in IOPS per core for those large block workloads. We start seeing clear gains starting at 16K block sizes. For those smaller block sizes, the 4K block sizes, ISA-L actually did pretty well. QDepth was one of the keys to really driving more work to DSA. And what that really adds up to is the higher the QDepth, the more value we saw for offloading to DSA. And then one of the things that came up as we were going through this benchmarking effort and comparing the performance and efficiency of using DSA to compute the CRC32 digest with ISA-L, the ISA-L function, was how good was this ISA-L function? How good was using ISA-L for our baseline for that comparison? So what we did to try and understand how good ISA-L was is we did a test where we configured the target application to use the CRC32 CPU instructions that are available in Intel CPUs. And we collected the IOPS and computed the IOPS per core and compared that to the numbers that we have for ISA-L. And basically, what we saw is with ISA-L, we were measuring over 20% more IOPS per core versus not using ISA-L and falling back to using the CRC32 CPU instruction. So what this means is that if you're not using ISA-L, you might actually see a little bit more mileage than what we just shared, because we compared against an ISA-L CRC32 function that is highly optimized using AVX512 instructions. If you would like to learn more, please join the SPDK community we are on a journey to build a framework for using hardware accelerators, such as the Intel DSA. The SPDK acceleration framework is designed for software-defined storage solutions. And what I mean by that is it provides plug-in modules that can be used in environments where hardware accelerators are not present. Also, Paul Luce will be talking more about the SPDK acceleration framework. So please listen to his talk if you want to learn more about the SPDK acceleration framework. Thank you.